So daily 2, number 68. Let me go through that in a moment. Okay. Just give me one more moment, please. All right. So daily 2, number 68. I'm going to share the screen. And let's just go over the premise of this. It says, find the electric force between two charges, one having a charge of 2.4 microcoulombs and the other 1.5 microcoulombs, that the charges are 0.22 meters apart. So here's the data, all right? So 2.4 microcoulombs, 1.5. We have to change these to coulombs before we apply Coulomb's law, okay? So remember, a microcoulomb is 10 to the negative 6, okay? So 10 to the negative 6. So we just, whenever you see microcoulombs, just change it right away so you won't forget. So 2.4 times 10 to the negative 6 coulombs and 1.5 times 10 to the negative 6 coulombs, right? Just change that just right away. Right away. Then when we apply Coulomb's law, K Q1 Q2 over R squared, we have 9 times 10 to the 9th Newton meter squared per coulomb squared. 2.4 times 10 to the negative 6 coulombs. 1.5 times 10 to the negative 6 coulombs, all over 0.22 meters. Don't forget to square that. And if you hit all the right buttons on your calculator, okay, thank you. If you hit all the right buttons on your calculator, then you should get an answer of 0.67 newtons. 0.67 newtons. Okay. All right. Okay, questions, comments on that? All right. Then the second one, sharing the screen once again, in case you've forgotten. The second one says electric field lines are drawn so they always begin on negative charges and end on positive charges. That's false. Okay. Let me go back to the electrostatics presentation. Here is the field around unlike charges. All right. Now, Michael Faraday invented this concept of a field, and he said the field lines are the trajectory that a positive test charge will take when placed and released in an electric field. Okay, so because it's a positive test charge, they always go away from a positive charge. All right, so by the definition of how he set it up, they begin on positive charges and they end on negative charges. Also, they never intersect. Okay, so when you're drawing these, and you'll have to do one of these on the upcoming test, and I'll describe that later. All right, you want to follow these rules, okay, and draw arrowheads on each and every line. All right, so that's the electric. Those are the electric field lines. Questions, comments? Okay, then I want to go over the daily 2 from Wednesday. All right, a wave that has a wavelength of 1.6 meters travels in deep water at 2.4 meters per second. They enter shallow water where they travel at a slower speed. What is the wavelength of the waves in the shallow water? Okay, now remember, the thing that does not change for a wave is the frequency. The frequency of a wave never changes no matter where it goes. So the frequency in the deep water and the frequency in the shallow water will remain the same. And that's going to be the key to solving this problem. So in deep water, V is equal to F lambda. I can find the frequency by dividing out the wavelength, and I get frequency is equal to V divided by the wavelength. All right, the speed was 2.4 meters per second, and the wavelength was 1.6 meters. All right, a little calculator work later will give you an answer of 1.5 hertz. So 1.5 hertz is the frequency. All right, so now the waves enter the shallow water where the speed is reduced to 1.8 meters per second. They slow down in the shallow water. What we want to find is the wavelength. Well, we can use V is equal to F lambda again, this time dividing out the frequency. So then the wavelength will be the speed divided by the frequency. So that's 1.8 meters per second divided by our 1.5 hertz frequency. Okay, a little calculator work will yield an answer of 1.2 meters. 1.2 meters. All right. Okay. Okay. And then the last one was, let's see, what was the last one again? The last one was, the speed of sound depends on the frequency of the sound wave traveling through it. That's false, okay? That's false. Now, let's say it were not false. Let's say it were true. What kind of implications would that have? Well, for one, we couldn't have concerts because because of the following. Now, most people would say, if they were going to say this is true, they would say that the higher the frequency, the higher the speed. That's the general trend. Okay, but if that were true, then the frequency or the speed that a piccolo, the sound from a piccolo that has a high frequency, that would be a high speed, whereas the sound of a baritone sax, would have a slower speed, right? Well, that would make concerts impossible, because if you were sitting far from the stage, then the piccolo sound would get to you before the baritone sax sound. They would never be in sync, right? So music, you couldn't have concerts because the music would never be in sync unless you were like immediately in front of the stage, right? So for that's a good way to remember it, is the sound does not depend on the frequency, because all the musical instruments, the sound from all the musical instruments, they all travel at the same speed through the air. All right. So the speed does not depend on frequency. It depends on the air. Okay. It depends on the speed that waves travel through media depends on the media. It doesn't depend on the wave. Okay. Okay. And those are the daily twos. Questions, comments? Questions, comments about that? All right, well, I want to go through the cost of power assignment, okay? The cost of power assignment that you guys did and turned in, and I looked at. It looked like you guys did a real nice job on that in general. I wanted to point a couple of things out about this. So I'm gonna go over this again, or go over this, and I'm gonna share the screen once again. And here's what I want this time, it's cost of power. All right. Now, I asked you to choose a couple of appliances. And so as an example, I'm going to choose a microwave that has 1100 watts of power. Okay, now, first of all, I wanted you to use a power equation to find the current. And in this case, the current would turn out to be 9.17 amps. Using that current to find the resistance, that is going to end up being about 13 ohms. Okay, now the reason I want you to get a little practice using the power equation and the Ohm's law, so I had you do that. Now, estimating the cost. Okay, I'm going to estimate that the microwave is used 10 minutes a day. Okay, that would make it 300 minutes for the month, or 6 hours. All right. Now, if I want to find the number of kilowatt hours, okay, I need to change the watts to kilowatts. Right. So I'm going to change that, move the decimal point 3 places to change it to kilowatts, and then multiply to find the number of kilowatt hours. And then this is an old, I forgot to change the cost essentially. So let's pretend that it's 13 cents per, and then the cost of operating the microwave for the month is 86 cents. Okay. All right. So that's one example. Another example that I used was a TV that has 150 watts of power. All right. Now, using the power equation, it draws 1.25 amps of current. Its resistance turns out to be about 96 ohms. And then how much does it cost to run? Let's say it's on for 8 hours a day. The TV is not on for 8 hours a day in my home, but let's just pretend that it is. It is in my parents' home, I'll tell you that. So let's see, 250 hours for the month. Changing the watts to kilowatts, that turns out to be 36 kilowatt hours of energy for the month. And that ends up having a cost of $4.68. All right, so that's the cost for the TV. Now, I was looking at some of the appliances that you chose. Several people chose a refrigerator. Okay, that's not a real good example to use because a refrigerator is not running all the time. Most of the time, it isn't. When it is running, the condenser in the bottom is pumping the freon through the coils and taking heat away from the inside of the refrigerator. That it's not on 24/7. Okay, it's only on a certain amount of time, and you would have to sit there for an entire day and time when it's on and when it's off. So that's probably not the best example to use. All right. And a real good example to use that I probably should have suggested is a light bulb, because lights are on in our home for a significant period of time. Okay, so if you did part 2 of the assignment for bonus points, that was very instructive. So let's check that out. Part 2. Let's say that I had a 60-watt incandescent bulb, which I used to have in my kitchen. Okay, and that bulb would be on 4 hours a day. The kitchen was right in the center of the house. So when I got home, after when the sun went down, I turned the kitchen light on, and it stayed on until we went to bed. All right, and so it was on for like at least 4 hours a day. All right, but I'll just pick 4 hours. Changing the watts to kilowatts, that is 0.24 kilowatt hours a day. And sorry, 87.6 kilowatt hours per the year. And that was the cost for the year of $11.39 that it cost me to run that light bulb for the year. Okay. Now, then compact fluorescents came along, and I can get the same amount of light, but only use 13 watts of power. So let's say I use that in my kitchen instead. That means that over the course of a year, it's only going to cost me $2.47. A cost savings for the year of $8.92, almost $9 per year, just for that one light bulb, by using the compact fluorescent instead of an incandescent. Okay. When I did this calculation, I went and switched out all my incandescents because it was costing me too much money. And then if you consider how many bulbs there are in your home, and then I had you go around and count the number of bulbs. Let's say you had 100 light bulbs in your home. One thing, you'd have a very large home, but 100 light bulbs times $8 and $9, that's $900 almost in savings that you would get from using compact fluorescents instead of incandescents. Okay, so if you have any incandescents in your home, you might want to show your parents this example and say, hey, let's go get compact fluorescents, or better yet, LEDs, because they're even better than compact fluorescents. Okay, $9. Now, a bulb doesn't cost $9. So these bulbs are going to pay for themselves in less than a year. Okay, so you might want to show your folks this example, and you too. Incandescents are so 20th century. They still sell them. People still buy them, but they cost a lot to use. All right, so get yourself LEDs instead. All right, you save a lot of money. All right, and that was the cost of power assignment. Questions, comments? Oh, okay. Rolling right along, I want to do the post lab on series and parallel circuits. Okay, I want to do so get that lab out, okay, or open it in a tab if you have it in your drive or something like that. I'm going to give you a few moments to get a copy of that. Get your copy. Then I want to run through it. Now, most people, there were a lot of people that got all 4 parts correct, and that was awesome. There were some that weren't able to quite. So I want to show you what you should have seen. Okay, so I'm going to share the screen once again. I'm going to do this a lot today, so apologies in advance. I think that's it for this. Yeah. So get back up to the top, reset, and then I want to do that. So here is the first part, and this is going to be part 1, the series circuit. Okay, and we're measuring voltages. So closing the switch, if I measure, current is running. All right, if I measure the voltage of the first light bulb, okay, I get 2 volts. Okay, measuring the voltage of the second light bulb, we get 2 volts. Measuring the voltage of the pencil, we get, oops, I have them switched. I get 5 volts, okay? So 2, 2, and 5. And then measuring the voltage of the battery, okay, what we get is 9. All right. So which statement is correct? The voltage across each resistor is the same as the voltage of the battery, or B, the sum of the voltages equals the voltage of the battery. And that is going to be statement B. Statement B is the one that's correct. All right, is the one that we see. Okay, and then moving on, next thing we want to do is we want to measure currents. So get my circuit back. I don't need the voltmeter anymore, so I'm going to put it away, and I'm going to get the current meter. Now, the first place we want to put the current meter, and I'm recreating, let's open the switch. I want to put it right here, okay? Right between the battery and the switch, because that's where it is in right here, in this diagram here. All right, and when I close the switch, I measure a current of 0.2 amps. 0.2 amps. All right, and now next I want to place it, then put the ammeter between the light bulb. So right there, or right there between the light bulb. So let's do that. I'm going to cut this connection, cut that connection. I'm going to put it, let's see, let's reestablish that. Let's get some room here. Cut that connection. Okay, and put the current meter there, the ammeter, and get a wire and hook that up. Is it hooked up? And we get a current of, once again, 0.2 amps. All right, then we're going to place it somewhere else in the circuit. We're going to cut that. All right, I brought that wire along. Didn't necessarily want to do that, but okay. Then we'll reestablish that. Then we're gonna put the ammeter right here. Now we're gonna cut it, and I'm gonna place it right there. And so hook it up like that, hook it up like that, close the switch, and once again, 0.2 amps. Okay, and then finally, I'm going to cut it there, cut it there. Oh, I'm going to cut it there too, and reestablish this connection, and then I'm going to place the ammeter between the pencil and the battery, and once again we get 0.2 amps. Okay, so which statement is correct here? Well, I would say that the current coming out of the battery is approximately equal to the currents through each resistor. Okay, the current was 0.2 amps everywhere, so that's going to be statement A. All right. Okay, now, hopefully that's what you found. All right. Now, I want to, oops, I want to escape out of there a second. What I want to talk about a series circuit in general. Okay. So I'm going to share the screen once again, and we're going to talk about a series circuit. Okay. Now, here is a series circuit with the battery. There's no switch, but that's okay. And with 3 resistors. Okay. Now, before I talk about this, let's pretend that we're all in this room. Okay. And the fire drill. You know, they announce a fire drill, so we have to leave. Okay. And we all have to go to a certain spot in the parking lot, right? How many doors would each of us have to go through? Okay. Well, let's pretend our evacuation route is going not out the front door out into the hallway, but back into my stock room, you know, and then back to the, you know, go out there and then go back, and then there's a door back there that gets you outside, and then through the gate. How many doors would each of us have to go through? Well, 3. Okay, the one to get out of my room, the one to get out of the K building, and then the one to get out of the gate to the parking lot. 3. And if there were turnstiles, and let's say that's the only way we can get out, because that's what administration told us, you must take that route, right? And so that was the only possible path, right? And if there were turnstiles at each door to count how many people were going through each door, and there were 25 people in this room, right? The turnstile for door over there would read 25 to get out of the K wing, be 25 to get out of the gate, be 25. It would measure the same amount. And then let's pretend now. Let's say that one of the doors was locked and we couldn't open it, right? Well, the entire train of people stop. We can't get through, right? The way is blocked. Okay, well, that's analogous to a series circuit. Okay, in a series circuit, there is only one possible path for the current. If the current is coming out of here and it wants to get around the circuit to the other terminal of the battery, it has only one way to go. Okay, and if there are 25 charges that come out of that battery, 25 go through resistor 1, 25 go through resistor 2, 25 go through resistor 3. It's the only, they have to, because it's the only way to get around. They have to go through all of them. So that means the current is the same everywhere in a series circuit, as we saw in the lab. And when I showed you the circuit, when I wired up a series circuit earlier, when I unscrewed one of the light bulbs in the other one went off. And this is analogous to a locked door. If the door is locked, then nobody can get through. The entire train of people stop. Okay. All right. So for that, if I have 3 light bulbs in series and I want one of them to be on, all of them have to be on. All of them have to be screwed in. Okay. Okay. Now, what about voltage? I'm gonna stop sharing for a minute. Let's pretend let's make an analogy with voltage and money. Okay. Let's say all of us have $10. All right. And at each of the 3 doors that we have to get out of, there's a guy there that's the toll taker. He says, you want to get through this door, you got to give me some cash. Okay. But the rule for this is, you have to go through 3 doors. So you have to give money at each door, and you have to end up with nothing. Okay. So, this guy at this door, he's big, but not that big. So I'm gonna give him $2. Okay. And so we all give him $2. So we each have $8 left. Okay. The guy at the second door he's a pretty big guy. Okay. He's gonna want, so we're gonna give him $5, right? And so we drop $5 at him. Okay, we give $5 to him. We have 3 left. 3 left to get to the last guy, the guy at the gate, right? And so we give him, and then we're out. So we have to drop money at each gate to get out. That's kind of like voltage. Okay, voltage is related to energy. All right, and the energy must be given. If I measure the voltage at each cross of these, they're going to drop voltage, right? And so that's what we found there. 2 volts were given to the first light bulb, 2 volts were given to the second light bulb, 5 volts were given to the pencil, and that's how much the charges had to come out. So they divvy up their energy between the resistors. These are literally called voltage drops. So they came out of the battery with 9 volts of energy. They dropped 2 in the first light bulb, another 2 in the second light bulb, and the last 5 in the pencil. Okay, so the voltages in series the voltage drops in series add to the voltage of the battery. Okay. All right. Then let me see. I'm going to get out of here. All right. And then we'll just get back into, there's a resistor relationship that I'm not going to cover this year, so don't worry about that. All right, now let's talk about a parallel circuit. Second part of the lab, we talked about a parallel circuit. And the first thing we did was we measured the voltages in a parallel circuit. All right, so let's do that. Let's close the switch, okay? And we measure the voltage across the first light bulb, and we get 9 volts. All right, measuring the voltage of the second light bulb, we get 9 volts. Measuring the voltage across the pencil, we get 9 volts. And measuring the voltage across the battery, we get 9 volts. Okay, so let's open the switch. And now which statement is going to be correct? And that's going to be statement A. The voltage across each resistor equals approximately the voltage across the battery. All right. All right, and then the last thing we did, and this is the trickiest one. So hopefully you have a little more experience with hooking these things up, a little more confident. This is the toughest one, and this is the one that people got incorrect the most often. And frankly, I expected that, because this is a tough wire. This is a tough thing to hook up. So I want to help you with this. So I'm going to take the voltmeter out. I don't need that anymore. Put that away, and let's grab the current meter. Now, the first thing that we want, oops, that's not right. The first thing I wanted to hook up was this one right here, and to put the ammeter between the battery and the switch. So let's do that. Let's put it between the battery and the switch. Okay, so get some room here. Cut that. Put it between the battery and the switch. Close the switch, and I get 2.16 amps. Okay, 2.16 amps. Okay, then what we want to do is we want to place it right here. Now, let's look at the circuit. What we want to do is to measure the current only through this first light bulb. So I want to wait for the charges to come out of the battery, assume the switch is closed. I want to wait for the charges to come out of the battery and go through the second light bulb and the pencil without having to go through the ammeter. However, if the charges go through the first light bulb, they must go through the ammeter. Okay, this is the tricky wire. This is the tricky thing to wire up. And the way I'm going to do that, first of all, I'm going to get that ammeter out of there. Okay, get it out of there. Get that wire out of there too. And I'm going to reestablish this connection. And what I'm going to do is I'm going to cut these wires, and I'm going to make a connection out here. Okay, and now I'm going to put the current meter between this junction and the light bulb. So let me do that, and let me do that, and then I need another wire to do that. Oh dear. There. Now, once I close the switch, the charges can get to the other light bulb and the pencil without having to go through the current meter. However, if they go through this light bulb, they must go through the current meter. What I get when I do that is 0.9 amps. 0.9 amps. All right. Okay, now I want to measure the current that only goes through the second light bulb. So I'm going to cut this, take everything apart. Oop, oh dear, get that out of the way. All right, get that out of the way. Cut that out of the way. Reestablish this connection, what I had before. But now, oops, now I want to do the same thing with this second light bulb. I want to measure the current only through that second light bulb. So I'm going to put the current meter right here. Okay. And so, let's see, how can I do this? That and like that, and then that and that. And when I close the switch, what I get is 0.9 amps. Okay. All right. And that's the current that's only going through the second light bulb. All right, one more thing to do, and that's measure the current going through the pencil. So I'm going to cut this, cut this, cut all this stuff, and get it out of the way. And actually, I'm going to just reestablish this, and then put the current meter right here. And now, okay, the charges can go through the first light bulb back to the battery, through the second light bulb, go back to the battery. Okay. But if I go through the pencil, I must go through that current meter. When I do that, I get 0.36 amps. Okay. All right. Okay. So remember what we had: 2.16 amps coming out of the battery. 0.9 go through the first light bulb. 0.9 go through the second light bulb. 0.36 go through the third light bulb. So which statement is correct? And that would be B. The sum of the currents through the individual resistors equals approximately the current coming out of the battery. Okay. All right. Now, let's make an analogy with this. Okay. Now, let's say that we're doing, it's work time. People are back at the lab tables. They're just kind of dispersed evenly throughout the room. All right. All of a sudden, Darth Vader drops out of the ceiling with the lightsaber drawn and he wants to chop our heads off, right? Well, we're all going to bail. We're all getting out of here as fast as we possibly can. And so now, if you looked around this room, how many ways are there out of this room? Well, there's a door over there. Okay, that's one. There's a door over there. That's two. And then there's a door back to my stockroom. That's three. 3 ways out of this room. Now, are all of us going to go through one door? Are all of us going to go through that door over there? Well, no. If you guys are all getting out of there, I'm going out of that. I'm going out that one, right? We're just bailing, right? So the 25 people in the room, maybe 8 will go out that one, and maybe 8 will go out that one, and then the remaining 9 will go out that one, right? So there's more than one way out of this room, right? Well, that's analogous to a parallel circuit. All right. Let me get back to my PowerPoint now. All right, which is right here, I want to say. No. Oh, I don't think I ever closed it. So, oh, it's right here. Okay, get past this. Parallel circuit. Okay, now if charges come out of this battery, they have more than one way around the circuit. They can go through resistor 1 to get back to the battery, or resistor 2, or resistor 3. There's more than one possible path for the current. Okay, and if 25 charges come out of that battery, not all of them are going to go through the first resistor. Some are going to go through that one. Some are going to go through the second one. Some are going to go through the third one. But if we add up all the ones that go through, it's going to total the current coming out of the battery. Okay, so the current is divided between the resistors, and that's what we found in the lab. 0.9 amps went through the first bulb. Of the 2.16 that came out of the battery, 0.9 went through the first resistor, 0.9 through the second resistor, and the remaining 0.36 went through the third. Okay, so the current is divided. All right. Okay, now what about voltage? Voltage is like money. Okay, you got $10. You know, you're bailing out of the room because you don't want Darth Vader to chop your head off, but there's still a guy at the door saying, "Hey, I want some cash." And if everybody had $10, the rule is you got to end up with nothing. So those of us who go through that door over there have to give all the $10 to that guy. Those of you who go through that door, all the $10 to that guy. Okay. So the voltage, if you only go through, if the charges only go through one resistor, they give all of their energy to that one resistor. Okay. And so the voltage is the same everywhere in a parallel circuit. Okay. Now, if you noticed, and I think I pointed it out, I was sharing. I want to get out. I want to escape this. Okay, and get back into the. What happened to it? Get back into this. Notice that in a series circuit, okay, the lights aren't very bright. Okay, however, in a parallel circuit, they are. Why is that? Well, because in a series circuit, they had to split up the voltage. They only got 2 volts of energy in a series circuit. Each of them only got 2 because they had to split it up amongst another light bulb and a pencil, right? Well, however, in a parallel circuit, they got all of the charges that went through them. They got all of their energy, so they're brighter. Okay, because the voltage is the same everywhere in a parallel circuit. Okay, so that's what I wanted you to find out to learn about series and parallel circuits. All right. Okay, switches here. Questions, comments about any of that stuff? Questions, comments? Okay, question. How do we want to wire our homes? Do we want to wire our homes in series, or do we want to wire our homes in parallel? Well, the answer to that is, well, let's say our living room was wired in series. Okay, let's get the implications of this. Okay, so here's my series circuit, and I actually want to cut this pencil out because I want to just talk about lamps. Okay, let's say that your house was wired in series, and you wanted to turn, and you turn one light on in your living room. Okay, and it's nice and bright. Okay, whoops, it's nice and bright, right? Okay, now you want to turn a second light on. You want to turn a second light on. Turn on another lamp in your living room. Now it's half as bright because because now the voltage is split up between 2 light bulbs, right? And then, okay, open the switch. Let's say I wanted to turn on a third light. Okay, let's say I wanted to turn on a third light. Now they're dimmer still. Now they only get 3 volts. So as you turn on more and more lights, the lights get dimmer and dimmer and dimmer and dimmer because they have to split up the voltage between each one. And if any one of them burned out, if the filament burned out, all of them would go out. Well, that doesn't make a whole lot of sense, I don't want to wire things in series. I want to wire them parallel, because then, if I turn, okay, break this connection. So if I want to turn, let me get rid of all this stuff. I want to get rid of that too. I just want to have light bulbs. All right. So let's say, where'd light bulb? Okay. So let's say I want to turn one lamp on. Okay, great. I get that. And let's say I want to turn another lamp on. Oh, great. And they're equally bright because they're all getting the same voltage of electrons. They're all getting the same. And so they'll be equally bright. So it makes sense to wire things in parallel. Okay. And it's a lot easier to engineer, because if I'm trying to engineer like a computer or something, the circuitry for a computer, and I know it's going to be in a series circuit, I never know what voltage electrons it's going to get. Is it going to get 9 volts, or is it going to get something else, depending on how many things are in the circuit? That'd be incredibly difficult to engineer. But if I know they're going to be in parallel, I know they're going to receive, in this case, 9 volts, and I can design my circuit accordingly. So it's much, much easier to engineer stuff when they're in parallel. What if a power strip were wired in series, with 6 plugs? You would have to have something in all of the 6 plugs for any of them to work. But no, power strips are wired in parallel. So you only need to have one thing. You can use one socket, or you can use 2 or 4 or whatever. Okay, so things are wired for that reason. Things are wired in parallel. However, there's a caveat to that. There's some, because it's convenient, it's easy to engineer, all that stuff. But we can get it can also cause us trouble. Okay, and let me describe why. Okay, so let's say this is your kitchen. Let's say this is your kitchen. It's all wired in parallel, right? And if I turn one, if I want to have my microwave on, that's good. If I want to turn on my kitchen stove, that's good. If I want to turn on my coffee maker, it's all operated on its own switch. And so it's all good. If I want something on, it's on. If I want something off, it's off. And it doesn't affect anything else. Very convenient. Okay. However, it does affect the circuit. Now, before I go any farther, I gotta talk about electricity. I gotta go into back up and talk about resistance a little bit. Okay. Let's say this is the wire. As electrons go through the wire, remember what resistance is. They collide with the particles of the conductor, right? We've been focusing on the electrons. Now let's focus on the particles of the conductor. When they collide with the particles of the conductor, they cause those particles to vibrate. And the more they get hit, the more they vibrate. And that vibrational energy, that kinetic energy, that manifests itself as heat. Okay. And the more they vibrate, the more kinetic energy they have, the higher temperature they have, and the hotter they are. So when electricity passes through wires, the wires heat up. Okay. Now, sometimes we want that, like in a toaster, for example, or a hairdryer. But a lot of times we don't. Okay, now let's go back to our circuit. And let's start turning things on. Okay, now that microwave is on, drawing 0.9 amps of current. Now I turn on the oven, and it draws another 0.9 amps of current. So the total current coming out of my power box is now 1.8. If I turn the more stuff I turn on, okay, the more stuff I turn on, the more current comes out of the power box, and the hotter the wires get. Okay, and this can be dangerous. Okay, where are the wires in your home? Where are the wires? Well, they're behind the wall, and they're stapled so they won't flop around. They're stapled to the wood studs. In most cases, wood studs in your home. And those wood studs are as old as your house, or older. How old is your house? 30 years, 40 years, 50 years? So that wood is very, very dry. Okay. And here's what can happen. If the more things you turn on, the hotter the wires get, and they can melt the insulation around the wire, and they come in bare contact with the wood. Okay. Now, and they can cause the wood to ignite. and then you have an electrical fire. And those are really dangerous, okay? Now, let me ask you a question. What time period in your home do you use the most electricity during the day? What time period? When during the day do you use the most electricity in your home? At night? Yeah, specifically when? The entire night or just certain periods, certain times of night? Dinner. Yeah, when you're cooking, when you're making dinner. Yeah, because you're using the oven, you're using the stove, you're using the microwave. Generally, you use the most electricity in that 6 o'clock to 7 o'clock time frame, something like that. Okay, and so that's when the most electricity is going through the wires. And here's what can happen. Here's what has happened. Using so much electricity, the wires get hot and they melt the insulation. And then they come in contact with the bare wood, right? And it causes the very dry wood to start to smolder, all right? But it doesn't ignite right away. Electrical fires are particularly dangerous for two reasons. Number one, they ignite behind the walls. So it's not like, if you have a gas stove and a towel happens to get in an open flame, you see that fire right away and you put it out. Electrical fires tend to begin, they start behind the walls and they're hidden, okay? And they can get very well established by the time the smoke escapes and gets to the smoke alarm. So they tend to be really well established before they're discovered. And another reason is they tend to happen at night. And when I say night, I mean like the middle of the night, because they don't ignite right away. The wood smolders and then it smolders some more and it smolders some more. And 3 hours later, it suddenly ignites. And by that time, everybody's in bed, and so you have electrical fire. By the time that happens, or when it happens, smoke alarm goes off at midnight or 1 o'clock. Everybody goes, oh my God, fire, and then you got to get yourself out of the room, get the kids out of the room, get the dog out of the house, get everybody out of the house, and you're at the curb, and finally you call the fire department. By that time, your house is half gone. So electrical fires are just particularly dangerous. Okay, so we have to protect ourselves, and the way we protect ourselves is with, and in general, to protect yourself from electricity overload, you use one of these. Okay, this is a fuse. All right, and a fuse, if you look very, very carefully, oh, I gotta get my finger out of the way. There's two metal contacts, and then, oh geez, how can I show this? Maybe you can see it this way. Can you see there's a little thin, it's really hard to see. There's a little thin wire. When you guys come back here next week, I'll pass these around. There's a little thin wire between the metal contact ends, okay? This is a fuse, all right? And I'm gonna put the fuse in the circuit. Yeah, I'm gonna put a fuse in this circuit of mine, and we'll see what happens. Oh, I'm gonna open the switch. Oops, open the switch, turn everything off. Turn everything on. And I'm going to put a fuse in here. Okay. And now we're going to start turning things on. And this fuse, notice I put it in series right next to the battery. So all of the electricity that's going through the circuit is going through the fuse. Okay. And as I turn more stuff on, more and more current goes through that little thin wire. And that little thin wire, when it reaches a certain current, will burn or melt. And that's going to happen right now. It burns or melts, okay, when it reaches a certain level. And I think this was rated at 4 amps. Yeah, it's rated at 4 amps. It's a 4 amp fuse. This one, I can't remember. I think it's like 20. This is a 20 amp. Oh, stop sharing. So this fuse is like a 20 amp fuse, okay? And it will burn or melt when the current reaches 20 amps, and it'll cut off all the current in the circuit. And it's a safety device. This is actually a fuse for some electronic instrument, maybe an amplifier or maybe a power supply or something, okay? Here's an example of a house fuse, okay? All right. What? Is it the thing that's switched off in an outlet if something short circuits? That's something else. I'll show you that. I'll describe that in a little while. This is a house fuse. Okay, not many houses have fuses anymore, to be truthful, but maybe if your parents have a workshop, like in a different building in your backyard, or a barn that you have animals in or something, they might still have a fuse box. And this is a house fuse. Okay, and it has metal ends, and there's a wire between them. At least theoretically. So I was wondering what this looked like on the inside, right? So I cut it open. Here's what it looks like on the inside. Okay, you can see the little wire contact between the metal ends, and that will burn or melt at this one's rated for 30 amps. Okay, you see that 30 there? So this one's rated for 30 amps. All right. So you can have a fuse that looks like this, or sometimes you have a screw-in kind here. Okay, here's a screw-in kind. If you look in that little window, get the light angle right, you can see there's a contact between the end and here, and all the electricity that goes through the two goes through that. Oh gosh, gotta get the angle right. Again, I'll pass this around when you get back here, but you can see that little. There's the angle. You can see that little metal connector that will burn or melt when it reaches 30 amps. See that 30 amps? Okay, so that's a house fuse, screw-in kind. All right. Here's a fuse for a car. All right. Here's a car fuse, and you have a fuse box in your car. Okay, and there's a couple of contacts with a little. Can you see it? There's a little Z kind of wire that will burn or melt when this reaches 5 amps. 5 amps. That's a 5 amp fuse. Okay. So fuses, and they protect us against circuit overload. Okay. Now, one bad thing about that, however, is when the fuse burns or melts, it's destroyed. You have to replace it, right? And that's not good. So I'd like to have something reusable, right? And so they now have things that are reusable, and those are circuit breakers. Okay, and this is an example of a circuit breaker. Okay, all right, and this is rated for 20 amps. Okay, it just says right in the button there. Again, I'll pass this around when you're here. And there's the contacts. Okay, so and it when there's too much, when 20 amps goes through this, the circuit breaker trips, right? And I was wondering why. I was wondering what one of these things looked like on the inside, right? So I took it apart, and it looks like this on the inside. Okay, and I learned a little bit about its operation. Okay, but to describe this, I have to ask you something else first. Toaster, right? How does a toaster? You put the bread in there, and it starts to heat up. How does a toaster know when to pop the bread up? Right? How does it know, or how does it do that? Most people would say a timer, right? But no, it's not a timer. Okay, toasters work in a different kind of way, and to show that, I got to show you a little demonstration. Okay. Okay, this is something called a bimetallic strip. Okay, it's a strip of metal that has different metals on each side. So you can see the coloration of this is different. That side is probably iron. That side is probably brass. Okay, watch what happens when I heat it up with this torch. Okay, safety glasses on, and I'm going to light this. Watch what happens to the strip when I put it. I'll get my backdrop of my shirt so you can see. What happens to the strip? It bends. Okay? Bends. Hotter it gets, the more it bends to a point. All right? Now, why does it do that? Because the different metals expand at a different rate. The brass expands more than the iron does, and so it bends. Okay, now I turn the torch off. When it cools down, which I can accomplish by just dousing it with water. When it cools down, straightens out again. Okay. All right. Well, there's one of these bimetallic strips in a toaster. Okay. And you can see it if you look at the bottom right there. Okay. And when you put the bread down, when you pop the bread down, oops, close. Okay, when you pop the bread down, the heat is generated and it toasts the bread and it heats that metal strip. Okay, when you do this, you're putting that strip under tension, right? And as it heats up, initially the bread gets most of the heat, but as the bread toasts, the strip gets more of the heat and it starts wanting to unbend, and it gets to a point where it wants to unbend, and it pops it back up and the toast is done. Okay, that's how a toaster works. All right, and you can change I don't know why this isn't closing. You can change the initial tension. Oh, that's why. You can change the initial tension by this setting. All right, so it'll pop up at a different temperature. All right, so that's how a toaster works. It has a bimetallic strip in there. All right, go check out your toaster. Not now. Well, this circuit breaker has one of those in here also, and it's located. This is kind of really hard to see. It's located right in here, right? Oh, sorry, right in this thing right here. Okay, so as the electricity comes in, it comes in here. Okay, goes through there, goes through that wire, and comes out the top. Okay, now circuit breakers are nice. So because if you want to like change a light fixture or something like that, if you want to just change a light fixture, you can just turn it off. Okay, and then the electrical connection is broken right up here. Okay, right up there, the electrical connection is broken, and so you change a light fixture, and then you go turn it back on, and you. Oh, this thing has been tripped many times. There, and then the contact is reestablished. Okay, all right, that's under normal operation. Now let's say you're in your kitchen and you turn on your microwave and you turn on your toaster and you turn on your oven and you turn on all this stuff, and finally it reaches a current of 20 amps through there, and then it will trip. Okay, that strip in there wants to go, and then it'll trip like that. Okay, and it'll break once that strip wants to bend or unbend. I'm not even sure which one it is. Probably bend. It'll break that connection between. It'll trip and it'll break the contact. Again, it breaks it right here. Okay. All right. Now, if it does that, the circuit breaker goes, oh, we blew a breaker. Okay, we got to go reset it in the 30 to 45 seconds that it takes to get for you to get from your kitchen to where your power box is. During that time, the strip cools down and it can be reset. Okay. Now to reset breakers, if you probably, in your young lives, you may not have done this, but you have to turn the thing one way and then you have to turn it the other way to reset. Some people are wondering why do you have to do that? Well, because this little prongy thing, that little point on the prong has to get back into here. There's a hole. Oops, wrong way. There's a hole in here, okay, which I can pass this around. There's a hole there that the tip of this prong has to get back in, and you have to turn it one way, and now that prong just got back in the hole, so that part is reset, and now I have to reset the electrical connection. I have to reestablish the connection right there, and so I go the other way, and now it's reestablished. So that's why you have to push it one way and then the other way to get it to reset. So let's trip this one more time. Okay, turn too much stuff on. Okay, now focus your attention on the electrical connection in the lower left. All right, just put too much stuff on. I trip this. Normally I do this with a camera, but oh shoot. Oh dear. See if I can do that for you one more time. All right, get this on camera. So focus your attention on lower left. Oh man, this is hard. All right, okay, see. Trips. And there, trip that connection at the lower left. All right. And then that little prongy thing has to get back into the plate. So I go that way to get it back in. Now it's in. Now reestablish the connection at lower left. And you're good to go. And that's a circuit breaker. Okay. They're reusable. Okay. I have tripped this thing hundreds of times and it still hasn't fallen apart. So Yeah, that's how a circuit breaker works. Now, those outlets with the buttons on it, a lot of times they're red and black. Those are called ground fault interrupters. Essentially, they have a circuit breaker inside the receptacle, inside the outlet. Okay. And so if, for example, in the old days, if you were operating your hair dryer while standing in 6 inches of water in your bathtub and you dropped the hair dryer, number one, you'd be stupid to do that anyway. But if you drop the hair dryer, you'd be dead. You'd be electrocuted. Nowadays, if you do that, the hair dryer will be plugged into one of those ground fault interrupters. Okay, and the circuit breaker the breaker inside will trip before it kills you. Okay, it will detect the surge and trip. Okay. You should test those once a year or so by pushing that red button just to make sure it will, because it'll create a short on the inside, and it'll just test to see if it's operable, which I don't know why it wouldn't be, but not a bad idea to test it anyway, once in a while, just to make sure it works. And by code, at least where I used to live, and I'm sure here too, if you any outlet that's within 6 feet of water, any outlet between, the electricity must go through one of those ground fault interrupters before it goes to any other outlet. Okay, the electricity has to first pass between one of those ground faults. Okay. So in your bathrooms and in your kitchen and in your laundry room, wherever your laundry is, you'll have one of those ground fault interrupters. Okay. It has to go through one of them. So it has to go through one of them first, and then you can go through regular outlets. Okay. When I rewired my house, I put an addition on my house in Wisconsin, and I wired it myself because it saved me $8,000. And but I followed code. I had to put one of those ground faults. That's the first place that the electricity went, and because I got to be safe. All right. So that's what that was. That's the thing. Yeah, that's switched off in and out. Okay. Generally, they have red, and I know they're in here somewhere. I just honestly haven't looked around to know where it is. Oh, there it is. Right down there. That outlet. Right. What I'm talking about is one of these. One of those ones with the red and black buttons. Ground faults. All right. So, and if you build a home, in your future, the electrician will be sure to do that, because I'm sure it's code in California as well. It's code everywhere. Should be, anyway. Okay. All right. So I believe, one more thing I want to show. It's in the presentation. Excuse me while I find this. Why can't I find it? Oh, that's what I want. Okay. So, I gotta get past some stuff. Some stuff that I normally do, but I'm not going to this year because of time. Yeah. Okay. So, yeah. So here's fuses. All right. This place. So a fuse is that's what it looks like. Okay. Thin wire heats up. When it reaches a certain value, the wire melts. Okay. So that's a schematic symbol for a fuse. Too much current and blah, blah, blah. Yeah. When the thin wire melts or burns, the current is cut off. Okay. Whoops. Sorry about that. Circuit breakers are reusable. That's a schematic symbol for the circuit. So, all right. And so that's it. Okay. All right. Questions, comments?
Just could you leave the slideshow up a little bit more to take notes on it?
Oh, sure. What did I do with it? Like that. Yeah. So that's that kind of puts a wrap on my electricity unit. Okay. Now we're going to end up having a test on this stuff, but I want to spend a lot of time reviewing because it hasn't. It's been a while since we talked about electrostatics, and I want to do it static electricity. I want to do a decent job of reviewing that. So my initial thought was to review Monday and Tuesday, and then have the test on Thursday and Friday. But I thought, I want a little bit more review time. So what I'm going to do is I'm going to review all next week, And then on the Monday and Tuesday before spring break, we're going to take the individual test in here. Okay. The collaborative test I plan on passing out next Thursday and Friday. Okay. And we'll have hopefully a decent amount of class time Thursday and Friday to work on it collaboratively. All right. And it's going to be due on the Tuesday night. Okay, for all my classes, whether you have odd or even schedule, the collaborative test is going to be due next Tuesday. All right, so you'll get the collaborative test. You guys will get the collaborative test next Friday. It will be due the following Tuesday. All right. Actually, you know what? Maybe because I want to give equal time, I'll make the collaborative test available on Thursday for everyone, whether you have the. Let's see, do I want to do that? Let me think about that. But we're gonna. There will be a sample test. I got one more thing to do, and that's talk a little bit about batteries. Okay, so I'm going to talk a little bit about batteries. Do my battery presentation on Monday and Tuesday. That's going to take about, I don't know, but that's going to take about 20 minutes, maybe. Okay, I'll talk about batteries, and then you'll have the rest of the time to work on the sample test, which is actually available right now in Schoology, but I'm not going to assign it. I've assigned enough stuff for you guys lately. I'll give you the weekend off. But if you want to get started on it, the sample test is in this week's Schoology folder. But we'll work on that on Monday during class. All right. The battery stuff. I always like to save a demo or two. I got another couple demos to show for for static that kind of keep in my pocket till review day, because otherwise review days are dreadfully boring if we don't have like a demo or two to do that. So we'll do that, and then we'll head into break. And then when we come back, we'll talk about magnetism, and from there go into light, and that's going to take the rest of the year. I really would like to build a Rube Goldberg machine, but I don't know if we can do that with these social distancing rules. It's one of the most fun things we do all year long, and I can't do it because of this stupid virus. But maybe I'll try to come up with something that you can do individually, although it's not nearly as fun individually. But anyway, so that kind of puts a wrap on the unit. Questions for me? I actually finished a little bit earlier than I thought I would. All these things, did I show you all the stuff that I wanted to show you? I believe I did. Yeah. Questions for me?